Hello, my name is Jessica Martinez, and I am a student in Calculus 150 BC. Today, I will be discussing how calculus is relevant and how it can participate in manufacturing of machine parts. To begin with, we need to discuss the axis of revolution, which is a key idea. If we want to determine the volume of a solid formed by revolving a region in a plane about a horizontal or vertical line, then it is called the axis of revolution. In many examples, the axis of revolution would be the x-axis, the y-axis, or a specific value in the x-axis or a value in the y-axis. The picture highlights the axis of revolution. In this example, the axis of revolution is the x-axis. The solid will therefore revolve around the x-axis, creating a solid of revolution. First off, the disc method or the washer method is a technique used in manufacturing parts for machines and other industries. To find the volume of a solid of a revolution, using the disc or washer method, then we can use the following equation. Volume equals the integration from a to b of pi times capital R squared minus the lowercase r squared. To be more specific, capital R is the distance from the axis of revolution to the far end, and lowercase r is the distance from the axis of revolution to the nearest point. Let's take a look at a real-life problem. In this example, a manufacturing company wants to know the volume of a solid formed by revolving the region bounded by y equals the square root of x and y equals x to the power of 3 around the x-axis. A key takeaway from this problem is that the axis of revolution is the x-axis. The first thing we will do is to graph the equations to have a visual representation of the region bounded. It is crucial to label the equations and the axis of revolution. In this case, the red line represents y equals the square root of x, and the blue line represents y equals x to the power of 3. Most importantly, since the axis of revolution is the x-axis, then y equals 0. Since we already labeled the known information, it is now time to draw a representative rectangle that is perpendicular to the axis of revolution. In this case, the rectangle is perpendicular to the x-axis. It is also important to label the x-coordinate of the rectangle, which is x. Now that we have drawn the rectangle, it is important to identify and label capital R and lowercase r. Recall that capital R is the distance from the axis of revolution to the far end. Therefore, capital R equals the square root of x minus 0, or simply the square root of x. Moving on, recall that lowercase r is the distance from the axis of revolution to the nearest point. So, lowercase r equals x to the power of 3 minus 0, or just x to the power of 3. To begin integrating, it is important to remember the disc washer method. Recall that volume equals the integration from a to b of pi times capital R squared minus the lowercase r squared. Once we have the general form, we can substitute it with the known values and information. Therefore, we will have the integration from 0 to 1 of pi times the difference of the square root of x and the power of 3 squared. Once we squared the values, we can obtain the integration from 0 to 1 of pi times x minus x to the power of 6. Before we begin the process of integration, it is important to note that pi is a constant. So we are allowed to move pi outside of the integration. This will make the focus the integration from 0 to 1 of x minus x to the power of 6. Now, it is crucial to have a background understanding of integration using the power rule. The power rule is as follows. To integrate x to the power of n, we have to add a 1 to the power of x and divide it by the new power. If the integral is not defined, then we add c as a constant. If we are given the integration points, then we can compute using the new function with the given values of x. Going back to our problem, we will then apply the power rule for integration. When we integrate x, we get 1/2 times x to the power of 2. When we integrate x to the power of 6, we will get 1/7 times x to the power of 7. Ultimately, we will get 1/2 times x to the power of 2 minus 1/7 times x to the power of 7. Since we know the integration point, there is no need to add a constant c. Therefore, we can now substitute in 1 for x and substitute 1 for x to the power of 6 and subtract to get the difference. So, we will get 1/2 times 1 to the power of 2 minus 1/7 times 1 to the power of 7. This gives us 1/2 minus 1/7. When we substitute in 0 for x, we will get 0. Hence, we will get 1/2 minus 1/7 minus 0. Now, the least common denominator will be 14. We will therefore get 7 minus 2 over 14, which gives us 5/14. Now, we cannot forget about the pi constant that we previously moved outside. Since we completed our integration, we can now multiply pi times 5/14. Ultimately, the volume of the solid is 5 pi over 14. Now, let's move on to talk about the shell method. The shell method is another technique that can be used in manufacturing parts for machines and other industries as well. The shell method is a calculus technique used to calculate the volume of a solid of revolution by slicing a solid parallel to its axis of rotation to create cylindrical shells. The shell method is used when vertical slices of the region being integrated are easier to describe than horizontal slices. To find the volume of a solid of a revolution using the shell method, then we can use the following equation. Volume equals the integration from A to B of 2 times pi times r times h. To be more specific, capital R is the distance from the axis of revolution to the rectangle, and d is the height of the rectangle. Finally, delta r is the width of a representative rectangle that will later be replaced by dx or dy. Let's take a look at a real-life problem. In this example, a manufacturing company wants to know the volume of a solid generated by revolving the region bounded of y equals the cubic root of x and y equals x to the power of 4 around the y-axis. A key takeaway from this problem is that the axis of revolution is the y-axis. The first thing we will do is to graph the equations to have a visual representation of the region bounded. It is crucial to label the equation and the axis of revolution. In this case, the red line represents y equals the cubic root of x, and the blue line represents y equals x to the power of 4. Most importantly, since the axis of revolution is the y-axis, then x equals 0. Since we already labeled the known information, it is now time to draw a representative rectangle that is parallel to the axis of revolution. In this case, the rectangle is parallel to the y-axis. It is also important to label the x-coordinate of the rectangle, which is x. Now we will identify and label r. Recall that r is the distance from the axis of revolution to the rectangle. Therefore, r equals x minus 0, or simply x. Furthermore, let's identify and label h. Remember that h is the height of the rectangle. So, h equals the cubic root of x minus x to the power of 4. It is time to begin integrating. As previously mentioned, the volume equals the integration from a to b of 2 times pi times r times h. Now that we know the values, we can substitute it with the known values. So, volume equals the integration from 0 to 1 of 2 times pi times x times the difference of the cubic root of x minus x to the power of 4 with respect to x. To simplify, let's rewrite the cubic root of x as x to the power of 1 over 3. Therefore, we can now multiply and distribute x to x to the power of 1 over 3 and x to the power of 4. This will give us x to the power of 4 over 3 minus x to the power of 5. Before we integrate, however, we are allowed to move 2 pi outside of the integration since it is a constant. Now that that's done, let's integrate with respect to x. Recall the power rule for integration is as follows. To integrate x to the power of n, we have to add a 1 to the power of x and divide by the new power. If the integral is not defined, then we add c as a constant. If we are given the integration points, then we compute using the new function with the given values of x. Hence, after integrating, we will get 3 over 7 times x to the power of 7 over 3 minus 1 over 6 times x to the power of 6 from 1 minus 0. Now let's plug in 1 and 0 and subtract the difference. When we plug in 1 for x, we will get 3 over 7 minus 1 over 6. When we plug in 0, we will get 0. So we need to find the least common denominator. In this case, the least common denominator is 42. This will give us a difference of 11 over 42. But we cannot forget about 2 pi. Now we can multiply 2 pi times 11 over 42. This will give us 11 pi over 21, which is our volume using the shell method.